Hello everyone, this is Pengfei from the Hong Kong Polytechnic University, currently carry out the research in Tencent Security King Lab, and today I'm honored to present our study, Too Good to Be Safe, Tricking Lane Detection in Autonomous Driving with Crafted Perturbations. First, about our motivation, we know that autonomous driving is developing very rapidly, and autonomous driving system is very safety critical. Here we have some news. For example, in May 2020, Tesla on autopilot crashes into overturned truck in Taiwan because the vehicle fails to recognize the truck in front of the vehicle. And in April 2021, two men killed in driverless Tesla car in highway in America. And also in May 2021, a Tesla in autopilot mode crashes into a parked police car. These facts are reminding us that the decisions made by the autonomous driving system may not be that reliable at the current stage, and it is very urgent for us to investigate the security of such systems. And here in my presentation, first, I have some backgrounds to share. First is about the lane detection and how this is involved in the autonomous driving. So basically, the images are collected by the camera on the vehicle, and based on the camera images, lane detection module generates the corresponding lane image or the corresponding lane output. And then the autonomous vehicle behaves based on the lane detection result. So based on these facts, changing the lane detection result, which is here, can affect the steering decision. For example, we can exploit its oversensitivity to create a fake lane if we can add some perturbations on the image to make the lane detection module believe that it is a real lane. And here we have an intuitive approach to finish this task. For example, here on the ground, the attacker manually add perturbations and then check whether the module will be affected by checking the output. And if not, the perturbation should be changed or relocated by the attacker again. So unfortunately, such an approach is very labor-intensive and error-prone because it is more like a try-and-error method, and of course it will cost a lot of efforts. And to solve this problem, in our research we propose our two-stage attack to solve this problem. So our attack is divided into two stages, and in stage 1, first we add the perturbation to the camera image extracted from the vehicle, and to trigger the lane detection module, generate the corresponding output lane image. And after that, we formulate an optimization problem based on the visibility of perturbation and the visibility of the detected lane, and adopted heuristic algorithms to find the best perturbations. And after that, we deploy this best perturbation in physical world for evaluation. To achieve this goal, we are faced with three main challenges. And the first challenge is how to extract the data from the real vehicle, and in most cases, these data are not exposed to users. So to solve this problem, we conduct static and dynamic analysis on the firmware responsible for lane detection in the vehicle to collect our data, including the camera image and the corresponding lane image. And secondly, how can we add perturbations to the input camera image? This is a very this is a challenge because we want our attack to function in the real world, to be effective in the real world instead of just function as the digital image. So for the ease of deployment, we use 8 parameters, which form a vector X to represent the attributes of the perturbations. And we use the pinhole camera model and the undistortion techniques to map these perturbations on the digital image for our optimization problem. So specifically, these parameters includes the length and width representing the shape of the perturbation, and the 3 distances representing the location of the perturbation, and L delta G represent the intensity of the perturbation, and theta as the rotation angle, and n as the number of the perturbations. And at last, we have the last challenge, how to find the best perturbation. So to solve this challenge, we formulate an optimization problem to find the best perturbation. Specifically, we quantify the quality of the perturbation by the visibility of lane and visibility of perturbation. To be specific, the visibility of lane should be high in order to make the attack effective. And also, the visibility of perturbation should be low in order to make the perturbation unobtrusive or invisible to human. Then we combine these 2 parameters together to form the Sx to represent the overall score. And based on this overall score, we use the heuristic algorithms to find the best perturbation, or the perturbation with the highest score. So that's all about the details of our attack, and how can we evaluate our attack? So in the paper, we answered totally 6 research questions, and here I will detail the most important 2 questions. The first is, how efficient are these algorithms to find the best perturbation, and can we misguide the vehicle in physical world? So for the first question, we use 5 heuristic algorithms to find the best perturbations. And it turns out that we found PSO, which is the particle swarm optimization, is the most efficient one, and thus we use it in other experiments. And here is a demonstration of the best perturbation we found. So here in the first row, we have a clean image without any lane, and of course the corresponding output is empty without any lane. And after we add a perturbation which is only 1 centimeter wide, and then we feed this modified camera image to the lane detection module, then the module believes that there is a very obvious lane on the ground. So in Q1, in question 1, we actually answered that our attack is effective as the digital image. But can we misguide the vehicle in physical world? To answer this question, we deploy the perturbations in the crossroads scenario. Then we switch the vehicle to auto steer mode and let it pass the crossroad to see whether its control will be affected by our perturbations. Here is the picture demonstrating our attack. When the vehicle is running on the correct direction, we use the physical perturbations to try to mislead the vehicle into the oncoming traffic. And actually, we found that the fake lane can successfully misguide the vehicle into the oncoming traffic. And here is the video demonstration about what happened during our attack. Please note that the vehicle is in auto steer mode, when recording, meaning that we do not actually steer by human. You can see that when passing the crossroads, the vehicle actually follows the fake lane into the oncoming traffic. To conclude, we conduct the first investigation on the security of the lane detection module in a real vehicle and review its sensitivity can be exploited to generate fake lanes and then even consequently mislead the vehicle. Also, we propose a novel two-stage approach to generate the optimal perturbations against the lane detection module. And we conduct extensive experiments on a Tesla vehicle to evaluate our approach. Also, the results show that the lane detection module in autopilot is vulnerable to our attack. As for the future works, we plan to assess other autonomous driving systems, including, for example, Apollo and OpenPilot, and we will try other attack methods as well. For example, try to erase the existing lane. Okay, thanks so much for your time.